My name is Ed Pegg Jr., and today I'm going to be talking about Narayana's cow problem, which is similar to the Fibonacci rabbit problem, but a few hundred years later. I'm Ed Pegg Jr., and I'm going to talk about various algebraic numbers such as Narayana's cow. So the basic idea is you have some points, and you move one of them to the origin, 0, 0. You move another to 1, 0. And then you try to figure out where the other points are, and if there's any nice pattern you can find with them. So here's an example of a hard problem, the ESCO unit distance graph. All these edges, yes, theoretically. All the edges in this graph are length 1. So this is a hard problem to solve. So one thing I found here with all these constraint problems is number fields were very useful. For example, this is an object called the Golem graph. The Haywood, I can't remember the name of it now, but the chromatic number of the plane problem is you try to color the plane, and you don't want any 2 points a unit distance apart to have the same color. And the question is, how many colors do you need? Well, if you have a triangle, you know that you need at least 3 different colors, since all 3 of those points are a unit distance apart. With this object here, if you toss it on a plane, you can show that at least 4 colors are needed. And there's a construction that shows that 7 colors is enough to completely color the plane so that no 2 points are a unit distance apart. So for a long time, the lower bound was 4 for the number of colors, and the upper bound was 7, and no one knew what the actual value was. And this is one of the graphs that proves that it's at least 7. So we have these odd values for the placements of other points. We've got 0 and 1, but these two look weird. So how can we make these points better? Well, we've got square root of 33, so we can try using 2 number field, and it doesn't work. But if you square the object instead, then you get this nice value. It's 7 over 72, 1 over 72. So I started squaring these values. And this set of points here, for something called Zacks Triangle, which I'll discuss later on, I found all these nasty root objects. If I squared all of them and used 2 number field, everything turned into these nice looking triples. So I wrote these functions to basically square objects and use 2 number field. And for the Golem graph, everything turns into these nice doubles. Everything is nice and smooth. And if you reverse them, you get the original values back. So I started looking, what other places is this useful? So here's the original graph here with the algebraic coordinates based on the square root of 33. So the first famous algebraic field is the golden ratio, which was made famous by Fibonacci. So here's his original text here. 1, 2, 3. Well, actually, I'm getting ahead of myself here. In order to understand the Fibonacci rabbits, you have to understand Arabic numerals first, which he introduced a few pages before he introduced the Fibonacci rabbits. So this is really an important book. This is what introduced Arabic numerals to Europe. And this is like David Singmaster sent me these photographs from the original book. So you have this sequence of numbers, the Fibonacci sequence, and the convergence converge to the golden ratio. And those are useful for things like building polyhedra. All of these are based on the golden ratio, which lives in the icosahedral group, which is also based on the golden ratio. You can also do other things with the golden ratio, like here's our first fractal here, the almond chair. These numbers on the edges here, these are all powers of the square root of the golden ratio. So this is the square root of the golden ratio to the power of 5 is the length of this edge. So you have this chair object divided into two similar chair objects that have the exact same ratios. If you want to solve the 4 in a line problem, here's a method with the golden ratio based on points of a dodecahedron and its diagonal intersections. For the 3 in a line problem, this was recently solved by, I can't remember his name, but there's 4 sporadic solutions for this 3 in a line problem. And here are 3 of them right here. All of them use the golden ratio. And the middle one here are the points, and everything is based on powers of the golden ratio and combinations. You can use the golden rectangle, an infinite number of scaled copies of itself, to get something with the same area as the original golden rectangle, but you can't actually exactly cover the golden rectangle with golden rectangles. One thing you could do is use the golden triangle instead, but that scales down really fast, so you can't really see what's going on. Another thing you do is Penrose tiles, which is, this is actually the Wyndham-Guerra roof. This is 3D, and all these ROMs are identical. You can also do the Klebb surface. There's 27 lines, and all of these points here are based on golden ratio values. So the golden ratio is pretty powerful, but I found that cow was more powerful. So the cow problem is that a cow gives birth every year. In turn, the calf gives birth to another calf when it's 3 years old. So this is a problem from 1356. So you need this polynomial here to solve the problem. It has a discriminant of minus 31, which I'll discuss a little bit later. And the radical form of this is terrifying. But it's approximately 1.46. And there's also the complex values here. So if you take it as a linear recurrence, you get the number of cows. This is the Narayana cow sequence. And if you round cow, you get the same sequence. Now, if you do something called the chaos game, where you use the complex values as directions and you pick them at random, you wind up getting this distribution of points when you play the game on, and you wind up getting these fractal triangle-like objects. Well, it turns out you can directly build these fractal triangles. So we've got the whole thing, and we've got 2 subcopies, which are identical to the original fractal triangle. And if you look at the area ratios, these are them here, they turn out to be exactly powers of cow for their area ratios. And these are really weird tiling objects. Here's how to build a nautilus with fractal cow triangles, which is something I managed to come up with that had never been seen before. So with the fractal, with the golden rectangle, we weren't able to build itself with that. So are there other values where you can have an infinite series of scaled things which add up to the original thing? Well, these are the values that might work, this table here. And it turns out, yes, you can exactly cover the original cow triangle with an infinite number of copies of itself. And this has never been seen either. Now, the discriminant is the product of the squares of the differences of the roots. And so that's that here. For any of these algebraic numbers, there's many different polynomials which basically give the same algebraic number field. So if you take the discriminant, you'll always get the same value. So that's a good way of knowing which field you're in. So here's two different polynomials. They're basically the same thing. They wind up with different values, but their discriminants are both negative 31. So this is the cow algebraic number field. So another famous one is based on the square root of 2. Hippasus made this famous and then was killed, unfortunately, because they didn't like the fact that they proved it was irrational. So A4 paper is based on the square root of 2. If you fold it in half, you get two similar rectangles. This is also the same algebraic field used for making the regular octagon, and also all the intersection points. And here's how these intersection points look as tuples within this algebraic number field. You can also divide a piece of A4 paper like this, which has never been seen before. I found this while trying to build these rectangle constructions, and I noticed, that's interesting, and no one had seen it before. So this is basically a complete list of squares and double squares, that all similar rectangles that are similar to the A4 paper. And this scales up into 3 dimensions. You take a cuboid, you cut it in half, and you get two similar cuboids to the original cuboid. This has never been published before. The first publication was this toy called The Fifth Chair by Dale Walton, which he published a few years ago. And it looks like this. You've got this chair-shaped object that's divided into 4 other chair-shaped objects that are identical to it, similar to it. And this was the first time the Delian constant, the cube root of 2, got used for this particular fractal issue. Now, I managed to find many other mathematicians who had solved this problem themselves, but they didn't think it was a new thing, so they all just let it sit in their notebooks. And there's at least 20 different mathematicians that have found this, well, this cuboid up here, that didn't publish it. So this toy is probably the first publication of this rather amazing object. So the next in the series, we've done the golden ratio and the silver ratio. The next we can actually solve, it's something based on the square root of 13. It is the bronze ratio, which is a solution, the best known solution for the ABC conjecture is used right there. If you look up ABC conjecture, you'll find that this is the best known example. You can also use it if you put 8 points in a unit square and you want the smallest triangle to be as large as possible, you have to use the bronze constant. And these 2 red lines here, they have a ratio to each other that's exactly the bronze ratio. Now, another one of the really powerful ones is the plastic constant. And this is the one where I found the most solutions in. Here's a way of dividing up a square into 3 similar rectangles that all have ratios based on the plastic constant. And the value is about 1.324, and it has a discriminative of minus 23. So if you hit a discriminative of minus 23 when you're using these techniques, you know that you're in plastic space. So we've got the Pentagons sequence, which this is based on. You can build more cuboids spiraling out forever, and that's called the Pentagons spiral. And I mentioned a set of points of the sort Zacks Triangle. This is Zacks Triangle here. You've got a triangle which is divided into 6 similar copies of itself. These values on the edges here are powers of the square root of the plastic constant. And there's 2 different ways of building this triangle from similar copies of itself. And we have a fractal triangle based on this. It has two different similar copies, and they're scaled as in powers of the plastic constant. And we get this infinite series as well, which had never been done before. Here's another set of 5 points where all the edges here are powers of the plastic constant. And this is a very weird configuration. So I figured, what happens if I go to 3D? I found out that I could build K19, 19 points, where all distances between points were powers of the plastic constant, which apparently hadn't been known. And as a side note, here's this weird polynomial where the coefficients are the same as the roots. There's only one solution, you need the plastic constant for it. For the square root of 3, there's two recent pieces of news. This 15th way of tiling the plane with pentagons was just found a few years ago by some friends of mine, actually. And also, it's possible to divide a square into similar non-right triangles. This is the only way to do it with 46 or less triangles. I actually paid for this solution. I had a contest for whoever could do it with less than 100 triangles, they would get that number of dollars minus the number of triangles they used. So I had to pay $54 for this solution. The 12er root is a solution to two problems using 12. If you want 12 circles to cover the maximum possible disk, you need this constant, and that's the solution. If you want to make the largest possible small triangle for 12 points, you need the same constant. I'm not sure if it's just coincidence or something else. For the Fibonacci constant, it's kind of the extension of the Fibonacci sequence. Instead of adding up the last two values, you add up the last three. And this value is used for making the snub cube with this polynomial up here, d to the third, blah, blah, blah. If instead of 1, you use the golden ratio instead, like this, you can get the snub dodecahedron instead. And that's a order 6 polynomial. The second Poisson number, well, what is the Poisson number? These are the roots of this polynomial here. You've got 1 point outside of the unit circle and 3 points on the inside of the unit circle. And that's the definition of a Poisson number, when there's only one root on the outside of the unit circle. And this is the second largest one. There's one that's lower, the plastic constant is lower. That's the only one that's lower than this one. And similar to the plastic constant, it leads itself to this bizarre similar triangle construction. All these numbers are powers of the square root of the second Poisson number, which hadn't been seen before. You can also build things called degenerate simplexes, where you've got 5 points, which are all at a constrained distance apart. And these numbers here, they're all powers of the square root of the second Poisson number. Now, I thought I might be able to find more large values, and here's a table of things I looked at, and everything with a power higher than 4 seemed to be single purpose. It was good for one thing and one thing only. This fourth one, the second Poisson number, this is the highest order algebraic number that I found had widespread applications. Now here's a simple matrix which has this particular eigenvalue. And when Brilhart looked at this in 1965, he noticed that the continued fraction was bizarre, and he didn't understand why. So it turns out the reason why, here's an example. We'll take a look at a similar root that's in the same number field. This discriminant's the same. Raise it to the 24th power minus 24, and compare that to e to pi times the square root of 163. And you can see that the numbers are very close to each other for 32 decimals of accuracy. It turns out that the first one is used to make the Leach lattice, and the second one is used for the J function. The connection between these two was called monstrous moonshine by John Conway, and Bouchards proved the connection between them and won a Fields Medal because of it, using modular forms. I'm pretty sure this whole talk is just a trivial extension of modular forms. It's just taking the square root and squaring. The silver constant, if we take a look at triangulated graphs and look at their polynomials, you get these points here, and Berara noticed there was clusters around first the golden ratio in green, and this red value here, which is now called the silver constant, not the silver ratio. It's a different thing using silver. This is also the same space as the heptagon. The regular heptagon uses these values. The last sporadic 3-in-a-row solution uses these points, all in the space of the heptagon. I don't know why it uses the heptagon. And here's something else I found with the 7-gon, the 7-2 star, and the 7-3 star. You can nest them together to get this unit distance graph that has fairly incredible properties. Another unit distance graph that's more famous is the Moser spindle. That's in black here. The Golem graph, which I said at the start, is in blue here, and they overlap. So I wrote this demonstration to see how many overlaps I could get between Moser and the Golem graph. And this guy named Aubrey de Grey really liked this demonstration. He said, I think I can extend this and maybe solve the Hadwidinger-Nelson problem, which is the chromatic number of the plane. And so I corresponded with him, and he was correct. He solved one of the most famous unsolved problems in mathematics just a few months ago with this graph. Now, I made the mistake of thinking that the square root of 5 and the square root of 7 weren't important. And he proved that they were, and he used Mathematica to solve the problem. So the biggest mathematical result of this year used Mathematica. Oops, and it's right here. We can also look at rationals which don't have any algebraic numbers. This is the best known solution for 4 in a row, but these solutions are terrible. 24, 25, they're only on 2 lines. So I'm pretty sure somebody can find a better solution. The best way of packing tetrahedra was just found a few years ago. There it is there. Everything is a rational coordinate. On the other end of things, you have high-level algebraic numbers, and I found they're pretty much useless. For example, here's the algebraic space for Graham's little hexagon. Everything is huge. I found that the original algebraic roots were actually simpler to use. So in conclusion, whenever you have a set of points, try putting one at the origin and one at 1, 0. And then look at the root objects and look at their determinants, try squaring them. And if they simplify in the same way, you're in an algebraic number field. And you can probably simplify everything a lot and get things with these nice properties. So there's going to be a series of these notebooks that I prepared with. I've got like 10 times as much material as here. If anybody would be interested in those, you can email me and I can send you that series of notebooks. And I can take any questions.